whatever you've written.
Gotcha. So here it's only, it's also 5.
Yeah.
The same thing.
Yeah, that's part of the same thing.
But if I didn't write it up for this, then I wouldn't have to.
Right, yeah. Yeah, so when I kind of look at your labs, I'm looking at like, did you at least probably measure accurately, and then do you carry the sig figs? Then I kind of look at your math. So with that step,
Okay.
yeah.
Thanks.
That's always the hardest part of lab, is like carrying the sig figs. Elevator's out again.
Oh, really?
When I used it yesterday, it kept like shuddering when it reached
Oh,
the
no.
floor. I was like, I don't think it's supposed to be doing that.
All right, any questions before we get started? And then we have a midterm on Monday, right? So we'll try to do some review today. So don't forget midterm Monday. And again, you know, bother me over the weekend. I still owe you all notes, but you can always email me. So that's what my poor oceanography students did, and I told them, please bug me if I don't get the notes up, which I didn't get the notes up. So I saw their email at like 10:30 p.m., and that's the motivation that I need. So I'll try to hopefully get that up during lab, but I make no promises since things happen. All right, any other questions, comments, concerns? And then, I handed back paper. And yeah, I'll probably try to just get through the homework and stuff y'all handed me so I could get that back to you during lab, is my plan. Slowly falling behind on grading, but try to catch up. And you can always yell at me.
I just chapters 1 through 4.
Yep. Yeah, so our plan for today is we'll finish up chapter 4 here, just a little bit, and then we can review the rest of the time, do more practice problems, whatever. Handout. Oh, you already got one?
Yeah.
So that's for later. So before we get to molecular geometry, let's formally go over how to figure out the mass of a compound. And it's not too complicated. You can probably figure it out. It's pretty logical. But there's also something kind of cool that we want to point out. And so there's a reason how we got to everything. We could do the like I call it the derivation if we want to. But basically what they have done is, so if you notice, let's just look at this water example and note the correlation. So we could look at an individual atom or molecule. So this is for one molecule of water, literally. And this is just adding up the atomic mass units and of course multiplying the mass on the periodic table by our little subscripts, so however many, so 2 times 1.01. And here, this is where you can have, again, small discrepancies, right? You could look at your periodic table. I think it says 1.008, you know, whatever. I'm not too picky on this, just pick whatever, you know, you want. Same thing with oxygen, you could see this as 15.99, just again, be aware. But anyways, you add them all up, and then we get, so if we have our units of AMU, again, that's telling us that's one molecule. So add it up as one molecule. But then notice that they've done something, so they set the value basically of Avogadro's number, which we can go into what that all is. But they set it up such that the AMU and then molar gram amount are the same. So you can also say 1 mole of water has a molecular mass of 18 grams. And that's just like super convenient for chemists. And so again, the mole is just a unit that chemists use. We can go through the derivation if you want, or we can just accept this if you're happy about that. Or you can ask me later. Oh, and I apologize because I promised you a liquid nitrogen demo, but that didn't quite go through because Nicole from the main stockroom isn't here. And so it would have been on me to get the liquid nitrogen, but the place opens at 8. So I wasn't confident I could both get liquid nitrogen and then come back here and set up for lecture. But we'll probably do that when she comes back in like 2 weeks, I'm thinking. So we'll postpone that demo because I do want you to see it and it's pretty fun. All right. Sorry, I didn't want to forget about that. And so again, and basically why this is, we'll just go a quick explanation. They base it off of carbon. And so we have, right, our carbon 12. And so again, basically our 12.0, I can't read. I have to look at it here. And so again, 12.011 atomic mass unit for carbon. Then it's correlated to that 1 mole of carbon is 12.001 grams. So is that pretty simple enough? And you can also see this molecular mass. It's given in a lot of abbreviations, so it could be a molecular weight, formula weight, atomic weight. It's all the same thing, basically, is how much is either, again, 1 mole if you're talking about a mole quantity or 1 molecule. All right, so let's find the molecular weight then of just some compound. Trying to pick a fun one. Let's just do cesium fluoride, I guess. I'll pick a couple, so we'll do that one. punching. So let's see, do we have an answer for the first one, cesium fluoride? You can just shout it out. 151.900, and we could say grams per mole or AMU, again, depending what you're asking about specifically, usually grams per mole. So I assume we all got that?
Do we need to change the 903 to 900?
So you could have different numbers. So this is where, right, some discrepancies may occur from rounding. So if you have 903, that's fine. If you rounded earlier because you used less precise, that's fine. So 151.9 is also fine. All right, iron chloride, or iron 2 chloride, we should say. What do we get? 126.751. Everybody get that? Thumbs up. Somewhere in the vicinity. A few people recalculating. And then this last one.
Do we leave it as AMU or grams per mole?
Either one is fine. So it kind of depend on the question. Like if it's asking for one molecule, I was just asking for molecular weight. But honestly, they're used interchangeably. You know, as long as you understand AMU is 1 molecule, grams per mole is the mole quantity. And usually you work in grams per mole. So, and then this one, what do we get?
196.192.
So 196.192. Is that about what other people got? So a lot of people got 194.194. So I would have to redo the math. I don't know if this is just from rounding. Again, I probably wouldn't be too picky on an exam, especially if you showed your work. So, you know, just show 8 times 12 plus 10 times. And you could round, like some people round this just to 10, but maybe that's too much rounding. You know, whatever. You could use more precise values as long as I see the work. Emma, did you get the same number again, or?
No, I have 194 this
Okay.
time. I don't know how it makes 6 last time.
No worries. So yeah, just show your work so then on an exam, if a little typo arrow occurs, you know, I can follow your work. So yeah, I'm all about following your work, trying to give you credit. Feel okay about this?
What was the full question?
Oh, we were just
Oh,
adding up masses. So are we comfortable with this? I mean, it came in a little late.
yeah.
Yeah, we can talk about it after if you're still confused, but basically you just kind of add up all the masses of everything on the periodic table and make up the formula.
And wouldn't you divide it by something? Or am I thinking of a different thing?
I think you're thinking of something else.
Okay.
But we could talk about other stuff like the lab after.
Yeah.
So we'll get through chapter 4 first. All right, so for your class, so I passed out the Vesper shapes. And I really only expect y'all to know a few of the shapes. You have the full kind of cheat sheet, I'll call it, for your fun and reference for later. But for our purposes, and we'll go over examples of all these though, is we're just going to focus on these really 4 geometries. So trigonal planar, tetrahedral, trigonal bipyramidal, and bent. But that's just like a full cheat sheet with all the names on there and everything. And so we want to be able to like draw a Lewis dot structure and then understand what the geometry would be. And so Vesper structure is really the combination of Lewis dot and then just giving it a 3D structure. So does anybody have any guesses for trigonal planar compounds? We've talked about a few. We didn't identify their geometry.
Is it more like since you have 3?
Probably. So then, yeah, what might be a good 3-to-1 ratio compound?
Oh, it would be like one on the top, one in the middle, and then 2, one on the left and one on the right side.
So one on the top. I'm not quite sure. Can you name a compound? So she named NH3, but let's
Oh, yeah, my bad.
see what the problem or where NH3 really falls. And I'm going to kind of give away the answer. But so NH3 though, and so this is where we want to be. So don't focus so much on where I'm writing it. Let's just look at what I'm drawing. Right, so just drawing your Lewis dot structure for NH3. And so what do you notice about it though? Yeah, so it has a lone pair. And so really, if you look at your key then, and maybe I should put this. Exactly. So it's a 4 on the big number. So you guys caught on before I could even explain. So this is really a 4, and they use the term electron pairs. I just say that's like things attached to it.
So that would be a tetrahedral instead, NH3?
Well, it's tetrahedral for like what I would call the parent electronic structure, since, yeah, that would be tetrahedral, but then the NH3 itself would be, and I put it under the right category, but it would be trigonal pyramidal. And you can follow along, so if you go down to your 4 here, so you look at 4 electron pairs, and so tetrahedral is if it has all 4 things are atoms. And we can draw, so now you're already seeing, right, some examples. So the classic tetrahedral example is methane, of course.
NH4 then, or not?
NH4 would work, it's just a charged compound, but yeah, that would, so ammonium would work. Oops. So that's a tetrahedral compound. And let me finish drawing methane. So that's tetrahedral. And then back to trigonal pyramidal, follow the chart, and then so you see, right, they replaced it, and this would be, sometimes you see the abbreviation MX3E, and that's what they have, 3 bonding pairs, 1 lone pair, kind of means the same thing, X substituents, E's lone pairs. And then so that falls into the trigonal pyramidal. And you can kind of see why it's named that way. You know, chemists aren't too terribly creative. You have a triangle and a pyramid, so trigonal pyramidal. So let's go back. So we're trying to figure out trigonal planar then. So what might be trigonal planar complexes?
What does the BP stand for on the bottom?
BP is bonding pair, so that's when it's bonded to like an atom. So you have the right idea with the NH3, except now we have to think of something that's different electronically and doesn't have a lone pair, basically. So something with less electrons.
I mean, there's no demonstration. There's one in the book, but I didn't come up with it.
What is,
So we have to have one that's a double bond then?
or just less electrons? And maybe it just doesn't make, so it could be electron deficient is what I'm getting at, too.
Okay.
Yeah, because I mentioned them, I think, on Monday, some of these compounds, they're pretty reactive. See,
Do we find an element or a compound first, the trigonal planar?
it depends how you want to think about it. You could start at nitrogen and try to work your way backwards, or group 5 phosphorus, work your way backwards to have less electrons. But yeah, I'm going for the compound once you start kind of putting pieces together. Because there's a certain group that makes a bunch of trigonal planar complexes, is what I'm hinting at.
So would you need an element that has like, 4 valence electrons, or?
Well, if you have 4, then you might just get a tetrahedral case, right? Because carbon has 4 valence electrons. And we could do silicon tends,
Would you do alkalines?
so probably not the alkalines. I think you went too far now in the periodic table. Too far back, I mean.
Where did you get the chlorine from?
Huh?
Where'd you get the Cl from?
Oh, I just picked a compound, right? So, because you told me group 4, what about group 4? But group 4 tends to make a bunch of 4 bonded.
So would it be like aluminum trihydrogen or something?
Yep, that would work. So aluminum trihydride, right? Aluminum chloride, which we had mentioned in the naming one, that this was a weird one because you name it like an ionic compound, but it's truly a covalent. There's all these boron compounds too, but as you might imagine, so what's the problem with just having 3 bonds here? Yeah, so all these are 6 electron compounds. So 6 total electrons. And so boron does the same thing. So boron trichloride, or tribromide too. There's also triethyl boron, which looks like that. And all these boron compounds like burn green fire. And so why that is you can recognize, right, they're electron deficient, so they're going to react with oxygen pretty readily then to fix that problem, essentially. But yeah, all these, though, have trigonal planar geometry. And so like you all recognize, it's going to be your group 3s and then attached to whatever. And then there can be some other trigonal planars that we haven't seen. So this sort of situation, if you have like a carbon double bonded, you can have a trigonal planar. Oops, sorry. Which one? This one? This is just carbon with, it's R's stand for like any group. So it doesn't matter what these R's are. But the simplest example would be acetone. Oops. Let's try. Oh, come on. Stay with your partner over there. Oh my.
Do you mean by any reaction?
Oh, any like R groups, like any organic structure.
I have a question, like, we covered naming Tuesday, what happens when we have like three of them? Why am I bringing it up?
Oh, because we didn't cover that because once you start getting into like organic structures, then that's like organic naming and.
Cause like that CO, whatever that everyone's gonna be, because you said you know, how would you name that? Like say it was like chlorine, so CO2 chlorine.
Yeah, well, that's where things get really complicated because it's an organic structure. So then you have to identify the group. So then this is like a ketone.
Okay.
And then sometimes they have special names. So that's. I'm not even sure if there's compound. I mean, there's tons of compounds. But yeah, the naming gets really complicated really quickly. So this is acetone. So that's the simplest.
And, sorry, do the two, lines above the O, let's see.
These lines?
Yeah, do those count like two bonded pairs?
Yeah, so this is a double bond.
Double bond.
Bless you. And I can rewrite it one more time. So I should have drawn those lone pairs on the oxygen. I was just
So
kind of
they
going.
share 2 electrons then, right?
Yeah, so then,
Okay.
well, it's 2 electrons in each bond.
Oh,
So
yeah.
yeah, they're sharing a
So each
total of
side
4.
shares an electron for a total of 2.
Total of 4, but oxygen sharing 2, carbon sharing 2.
Oh, okay, yeah.
So they're each contributing 1 electron to each bond. My other point in the naming is there's like a whole organic naming. So these ketones, a lot of them end in like these "-one" endings. So like this is 2-propanone, but then people just call it acetone because that's its common name. Yeah. And that's also why in chemistry we have the caste system. And so, for example, every compound has what's called their caste number. And so this is unique to the compound so that you don't get confused by all their other names, as you can see.
Is the CAS number like some sort of system to keep all like the compounds in one area, I guess?
Or to keep them categorized, yeah. Because they organize them by the caste system, and then this is just like a more organized database, and it's tied to like the SDS then, because you want to make sure that you're talking about the same compound, and then we're testing it for like safety. And then of course people can add, their own substances. So if you make a new compound, you could add it to the registry so it gets a new number.
Can anyone have access to the registry, or does it have scientific institutions?
I think it should be open. I'm trying to find the link too.
There's only one way to find out, just Google it.
Yeah. I mean, the cast number is also like on everywhere. I'm just trying to find what they were. Let's look at this link. That's a web archive. Yeah, so it should be open. I'm sure you could search. Let's see how this works. Oh. Well, that's weird. Okay. I don't actually know how this website works. Usually people just go to so a big chemical manufacturer is Sigma Aldrich. So I've never looked at the CAS page officially. I probably should at least poke around. But if you just go to like any purchase site, you know, let's just type in acetone or whatever. And so it always has a CAS number, and then it should have, oh, come on. I must have to pick on a product. I'm trying to find the there it is. That's, okay, I won't sidetrack. But what I was trying to show you is once you click on the product, then you can get the SDS, also used to be known as the MSDS. Now it's just safety data sheet for some reason. And so we mentioned this in lab, and so, you know, it's always good to read the SDS, just see what it says. It's usually not. Yeah, kind of cool. All right, back to geometries. And so you could have other technically planar compounds. And so the hybridization for trigonal planar is called SP2 to kind of reflect the shape. And what it's kind of saying is if you have an S and two P orbitals combining, you would get the shape that looks like this. And so three orbitals combine to make three lobes. That would make this oxygen also an SP2 or trigonal planar. So all this is telling you as well is like the location of the lone pair. So they're going to be sitting planar. So this would be a planar molecule there. Other good examples, you could have, right, double bonded carbons. So if I draw benzene out, all these have H's. So every carbon itself, right, is trigonal planar, and that means benzene then is a planar molecule. So that's also what's helpful. And so other kind of weird bonding things, so you could have like nitrogen double bonded, and they would have a lone pair, so something like this. And I guess I can finish it out. Okay. But then this center here, and actually this one too, those are both sp2 planar as well. So does everyone kind of follow with that, what we're looking at, how we classify it, why they're all planar, and I'm using this language, sp2. Okay, no questions? All right, so then we looked at tetrahedral, and we gave some good examples. I like this charged ammonium. Any other tetrahedral examples we want to talk about? Any favorite compounds?
So what would H2O be, out of curiosity? What would that be labeled as?
Oh, not linear though. Yeah, so if we draw it out, yeah, so it's bent. And so you can see, so it falls under our 4-electron group again. I'll write that out. And so, right, you look at your cheat sheet chart over here, 4-electron pairs. But then, right, oxygen has 2. We could use their long language, 2 bonding pairs and 2 lone pairs. Or I would write it MX2E2 is another way. And then so you go over, and then so that leaves you as the bent. And let's just talk about one other bent structure. So just see if you can draw out what SO2 might look like, the Lewis dot structure. Just play with that.
So, I said it's like break down this, and then add on the oxygen. So, what I do is I take these two out and replace by bonded pairs between oxygen. And I do that for the full tank, bonded pair. I don't link to lone pairs.
Yeah, see, that's kind of weird for that one. That's why we're looking at this. I think you have to run an idea. So yeah, you put those 2 electrons in, maybe a double bond, and you have to play around with it too. And so you just want the total number of electrons to add up to be what you have. So you don't have to do some bookkeeping. Each are contributing 6.
So does the entire compound, it has to like fit in with sulfur's valence electrons and oxygen's electrons, right?
Yeah, so basically, at least what we should have established and the kind of where the question is going is so how many total electrons in this system? And so you just look at your valence electrons and they're both in group 6, right? So they're in the same group, so all of them are contributing 6 valence electrons. So we know we have 6 times 3, so 18 electrons. So now it's just how you write those on there. So we'll give people another minute or so to stare at this, look at it. Like, it's crazy hot in here.
What? I understand the 6 valence electrons, but where do you want the 3?
'Cause sulfur plus 2, yeah.
I'm trying to word this best I can. So the line, the bonded pair line, does that represent just like 1 electron for oxygen and 1 electron for sulfur?
If it's a normal bond, yeah, but it depends how they've bonded.
So essentially we're just replacing a dot with a line. It's connecting.
Oh, yeah, two dots of the line.
Oh, so it has to be 2 dots, can't be a lone pair, it has to be 2 dots?
Well, this situation might be different, but just in general, 2 dots equals the line.
Oh, okay, that's right, I definitely see that.
Yeah, because we may see weird scenarios where I call it homolytic versus heterolytic bonding, just homolytic, each one's contributing 1. Heterolytic, sometimes it's just one contributing
So the
both.
bonded pairs would then turn to a line, leaving the lone pairs, or leaving the lone pairs behind. Essentially,
Yeah,
right?
so usually the lone pairs don't participate in bonding, but
Okay.
I'm making a point with this one. Okay, so what do we get? Does anyone want to try to draw it out or tell me verbally? All right, go for it. Either way, you can draw it out. Oh, here's one marker on
There's
the
a
floor.
better one here.
We got, so it doesn't have a ring structure.
Oh, okay.
So what else do we get? We get something else. I should have gotten a hint that it wasn't a ring.
Got something, but not one.
Same here. I was somewhat idea, but not much else.
I'm not sure if the structure is there, but I really don't think it's are. The electron count is right.
We got some radicals on there though. So that's my criticism of that structure. Now how can we fix it though? So let's work with this
What are you
structure.
talking about radicals?
So you can't just normally have what
Oh,
little
the long
electron.
guys?
Yes.
I
So
did
those are
triple bonds,
you did triple bonds?
yeah. And then one lone electrons on each.
I think we have 18 electrons here too. Oh no, we're supposed to have 18, my bad. Okay. So what else could we do? So we need to get rid of a radical. So we can still start with this. You said you had a triple bond. Do you want to draw your structure and then eventually we'll.
Not really.
This is a good exercise though, because the point is we need to look at our structures and then figure out what's wrong with it and then how we can fix it.
Wouldn't the liner place the electrons for both for the oxygen and the sulfur? Or is there we're just counting purposes?
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I think it's just drawn funny because it's in the radical.
Oh, just for okay.
Yeah, so, you could, because these should probably be like over there.
Oh,
but-
yeah.
But we're still searching for the right structure. So 1, 2, we need to like combine them. So let's put them on the board. Yeah.
I don't understand any of this, quite frankly.
Well, no, let's go through it slowly because this is a really good exercise right now because we need to figure out what's wrong with these two structures, but then like where's the middle consensus is where I'm trying to get at. So I think you're getting the right idea, and I think I at least have. Oh, I'm missing.
Also
electron.
double bond it and add the extra lone pairs to the O's.
That's where we're thinking. That should be, yeah. So we're looking at both these structures so we can just identify what's the issue. So radicals here. And then I think you were saying sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which sulfur can be hypervalent, but this might be too much here.
Where are we getting the 14 at?
Oh,
I get that. I thought we were adding up to 18 total though.
right, 18 total, but we're just analyzing how much does sulfur feel. And so that's why I circled it with this highlighter, because sulfur feels all of these electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
Does that mean it lose many electrons then? Because shouldn't it only have 6?
Well, it wants to feel 8 for an octet, right? But sulfur could be 10 or 12 generally when it goes hypervalent, right? So we'll see sulfur, like sulfur hexafluoride, right? Let's think back to that. Except how many total electrons did sulfur feel in that case?
This is basically hers just double bonded instead of
Yeah,
double
I
bonded
think so.
with an extra set of lone pairs of oxygen.
Yep.
Yeah,
So that's,
but I don't know why. And I don't understand what.
well, it's,
Feel really lost. With what it's feeling.
okay, so, right, let's look at what it's feeling, right? So I circled, so what it feels, it's either the electrons that it's connected to or the lone pairs. And so I just circled, right, so, and I'll circle what everybody feels. Oh, come on, oh, whatever. Sorry, I forgot how to use my thing. So, right, oxygen feels all those, right, because it's connected to it. So it still has the octet. But yeah, this sulfur having 14 just might be too many. So I would raise a little red flag there of like, Because in other cases where we've seen sulfur hypervalent, so how many is it feeling, right? So look at each bond. So it's connected to 6 bonds. So did you follow how this one feels 12 electrons?
Yeah.
Okay. So then we're okay with that, right? So now looking at this is kind of a red flag because it's feeling too many.
A little crazy.
Yeah, so we might have gone too far. But so now I think everybody's kind of following that. Let's try double bonded and then now put those electrons on oxygen. Just do a double count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we're back at 18. We don't have our radical issue anymore, so that's good. Solve that. And we can double check. So this feels 8, and then this feels how many?
Meaning the S is still hypervalent with 10.
Yeah, but that's okay, right?
It's
So
more doable. It's more too low crazy.
exactly. So we're just trying to find the best structure, trying to balance it out. And the point is, right, let's analyze these structures and figure out kind of maybe what was wonky and how we can make it better, which is how we finally got at this structure. And so all of that was to say, this is another version of a bent geometry. And some people make the distinction between them, so this is also called bent. But notice the difference, and it's on your chart, so this would be under the 3 electron pair category. So 3, oops.
Real quick, so I realize where I made my mistake, and we're talking about that, I shouldn't have connected them. But why would it naturally want to become hypervalent instead of connecting the oxygens and creating like a circular?
There's probably ring strain issues with making a 3-membered ring like that.
Okay, because I figured oxygen connects to itself anyways, and if it's connecting to the sulfur, it wouldn't have an issue, but there might be something causing it to have issues if it does that.
Yeah. Yeah, and that's something that you would look at like OCHEM as like all the ring strains, and you compare, your 3, 4, 5. So it isn't until the 6-member ring where it, I think, alleviates a lot more strain. Yeah, even like squares are pretty strained. But that being said, there are a few ring things like epoxides with like O, C, C, but usually I should just give you a hint that they're not in a ring or they are in a ring.
Well, yeah, I should have figured that because we were talking about beneficial perspective.
Yeah, and then,
Yeah, yeah.
They always say like math and music are related, and you were doing this, and I like related it to like something musical. And it's like, now it makes sense, that kind of makes sense a little bit.
yeah, I mean, music's a lot of fractions, so maybe that's a good way to teach people fractions, maybe. Anyways, but I also wanted just to point out some textbooks make the distinction of V-shape bent or V-shape. And so that's how they differentiate between like normal bent, which is the water with 2 lone pairs, versus this 3 electron pair V-shape. Because they technically have different angles, and your chart covers that, but I probably won't be asking you about angles in this class. And so you can at least appreciate that this is a 119 angle, so a lot wider, versus this is 104.9, since it has the 2 lone pairs pressing down. Yeah.
So just to double check, the reason you had the one V-shape or V-shaped bend, with the double bonding lines, is to reduce the number of lone pairs in all the elements.
Well, overall, we're just trying to make the best structure that satisfies the octet rule for everybody. And then,
so every element has 8 then.
yeah, or at least,
Okay.
well, sulfur has 10, but it's better than the 14, or,
So it is it's just the closest possible to getting that rule.
yeah, essentially.
Okay.
And, again, metals are a different story. That's the 18 electron rule. We're just trying to draw, kind of our best structure. And some of this goes into, like, if we want even more detail, we have to study, the reactivity more. Then you can look at, the actual bond lengths, really describing, is it truly a double bond? Does the length reflect that? So you can really, get into it and analyzing it and comparing it, to other compounds. But obviously that's kind of beyond our course. But that's what, a chemist is into, right? Just really studying that bond, studying that nature of that relationship.
So like, you made this formula, and then a person who does that kind of stuff would look into it, see if it's actually a double bond or if it's something else.
Right, exactly, yeah.
Okay. How do they do that necessarily? Would they do different experiments with the compound, or is it using a chart or something?
Yeah, so you would have to do different experiments, right? But then you compare it to past data. So a basic thing is checking bond length. And so then you would compare it to all the known sulfur-oxygen double bonds. Does it match? Is it average? That's just the first question. What's the stretching? If you could measure, that vibrational stretch there. And this is kind of a weird compound to study, though, because it's sulfur and oxygens. But
can you have lone pairs in one of these compounds or no? Can you only have like bonded pairs?
No, you can, I mean, we have a bunch of lone pairs right here, right?
Oh, okay, I thought those were like bond pairs.
So any of these 2 dots, those are all lone pairs.
Oh,
Any
okay.
lines are,
I mean,
bonded.
like the single dot. Okay.
what do you mean single dot?
Like if there's only one dot instead of two.
These, that's why I
Yeah.
said we usually don't want these. These are radicals.
That's
Usually
okay.
radicals are unstable.
So those are the radicals. Okay.
Yeah. And you can have like radicals, you know, like the atmospheric chemistry, like that's where you get weird radical chemistry because the UV light will like break some bonds and you get a temporary radical species that does something reactive, but they're very short-lived for the most part. All right, so now let's look at what are polar molecules. And let's just compare, let's just think about 2 different cases.
Is this chapter 4 or chapter 5?
Oh, this is still chapter 4.
Okay, just one double check.
So which one of these molecules do you think is polar? What does it mean to be polar? And let's just take a minute or so to look at these.
Solid word words.
So any thoughts on either the definition of what it means to be polar? How do we identify polar molecules? Or even which one of these is polar, which one of these molecules is nonpolar, if any. Yeah, thoughts?
So polar is the separation of electric charge, and
So is that reading from your book definition then?
technically it's on Google.
Oh,
I haven't read the chapter yet.
So now let's put that in our terms though. So separation of charge, what are we looking for? What,
One has a greater pull to it.
all right, so we could identify, so are you telling me this carbon-chlorine bond is polar then?
I have no idea, I'm not telling you nothing.
So, but by separation, that would mean like, would that mean there's less of something because it's a separation of it? It's being separated because like bonding is like brings them closer together, but separating is like pulling apart.
Well, we can think back, where was our,
Thing to do with the negative
Because are you talking like the difference between like the covalent and the polar covalent?
yeah,
So which one's gonna be more polar than?
So more
oh,
separated
this is,
than that?
so we're looking at that, but then we're trying to figure out if overall, so we're kind of asking 2 questions. And so you mentioned charge separation, so yes, first we have to just identify the difference between a pure covalent bond versus a polar covalent bond. But then there's a second step to it when we actually look at the molecule itself. And that was my point in this example.
So it's polar like halfway. It's not covalent bond, but it's not an ionic bond either. It's a polar because it's in the process of becoming an ionic bond.
kind of, but we still consider it a covalent bond.
Oh, okay.
But, so right now, we could identify, right, that we have some unevenness in the bond. And so all I'm drawing here is the direction of kind of our polarity. I'm using the chemistry formal chart, or formal system, so physics is actually backwards. But I have the negative N pointing towards the more electronegative element, and I put my arrows, I put a cross on them or a plus sign to help remind me that, okay, carbon is more positive, right, less electronegative. But then what do you notice about all the forces of these polar bonds? Yeah, so they're going out in all even directions. And so basically the other way to analyze this is people kind of get confused, and it does get tricky. But if we're looking at like the 4-electron pair group, so this means it's the first one in the box, right? So fully symmetric. So all these first columns, right, are fully symmetric. And all that means is if it goes out in all those directions, then it cancels out and is nonpolar. Yeah, and so you use the term compound velocity, and so chemists would quantify that using the term, if I can find it, dipole moment. And so yeah, the same thing as what you're implying. And so overall, I don't know how they do this, if they do it experimentally or just computationally, we would have to look into it, but they determine the dipole moment. And so for this one, so this is carbon tetrachloride.
Wait, how did you determine their electronegativity? Was that just from a chart?
So it's from a chart, but I'm just looking at the general trend. So I can see that chlorine is right next to fluorine. And where's our chart? So here's our
And
chart.
that's where fluorine's like the most electronegative, right?
Yeah. So all the halogens are pretty electronegative. Yeah, so you can see that trend. We could also calculate the difference, right? If we're unsure of the trends and the guessing. If we go back,
You would just get that from the chart.
yes, you would just have to look at a chart. So I'm just doing the difference of those. And
You
so,
said this first column, they're all nonpolar because they're all symmetrical?
yeah, as long as, so anything that has that geometry is going to be symmetrical, as long as it's the same substituents, right? So it has to be the same, like all chlorine, 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 hydrogens.
So if it's all the same, it's not polar, but it's different, it's polar.
Right, so in this case, so now, follow me with your question. So now looking at this molecule, so this is chloroform. We'll just name it for ease. So chloroform, so now chloroform, do you think chloroform is polar or nonpolar? And so, right, we could draw it like this. You use the term, right, vector pool. So if you have vectors on the brain, that's a good way to think about it, right? Which way is it overall going, or do they cancel out? I don't know if that's helpful language or not. It kind of depends what you've taken in your background, but that's essentially what you're thinking of. Is there unevenness? It's another way I look to say it. Is a molecule uneven?
Slightly unrelated, but because of the charges, because positive attracts negative and then the negative repels negative, would this be like a perpetual motion machine because the hydrogen is being pulled towards the carbon, which is more negative, and the carbon is repelling the chlorine, which are more negative?
I mean, it's just, maybe there's a way to harness that. And perpetual motion machines, though, are thermodynamically, of course, not favorable. But what you're getting at is it is kind of attracting and chasing. So polar molecules are, though, cohesive, right? So they attract one another. And so that goes back to what we see water, where it like bubbles up and attaches everywhere. So it's of course superpolar and has hydrogen bonding, which we'll go into. But yeah, that's kind of the point. So you're kind of seeing it. And let's just quantify this then. And I just like showing you the number just so you can at least get a feel of things. So this has a dipole moment of 1.15. And let's look at water, because we know water is polar. So let's just orient ourselves. Man, every time I do a search live, it's like super slow.
You could say it's 6, or you could say it's 15. I have no idea what page is 1.15, like strong, or is it like, what's the scale for that?
It is fairly polar. I don't know the scale, but we should look at the scale. How come it doesn't have a dipole moment for water? I was trying to orient this with water. Let's water dipole. Oh, so this one, the net dipole moment, so that's what we're interested in, is 1.84. So these numbers are pretty small. So water, which is fairly polar, is 1.84. You know, then 1.15 is fairly polar. So let's look at dipole moment scale. We have a range. Oh, geez.
There's a formula.
Can we just have more examples of a range? No, that's too much.
Yeah.
Oh, look, vector.
I called it. I called it. Has to do with vectors. Knew it. Okay. It's trigonometry into calculus. That's what it is.
Oh, God.
It's not that bad, though.
Oh, my
But I
God.
hate statistics in that weird Greek
Trigonometry, like,
way.
online
So
school,
that's-
man, I learned
that's-
jack crap.
That's actual like entry. Well, that I would say that's like calculus level calculus.
I don't like it.
It's not that bad.
I had to do like a single lesson in homeschooling with it, and I hated every second of it.
I did trigonometry in online school, and it was like the worst thing ever, like.
I love trigonometry.
I learned
Well,
how
most
to
of
do
that is like vector calculation and basically doing difference of vectors and like the polar. That's mostly what that is. It's more trigonometry than calculus, but it has a big calculus.
Well, I don't know if this was much orientation. This at least gives you another kind of sense, because again, HF is a pretty polar bond, but then the dipole moment is at 1.82.
So I'm gonna say anything hidden two is gonna be this.
Yeah, I mean, that's what it seems like.
So 0 is non-polar, 2 is you're gonna blow up.
Yeah, I think 2 would be like ionic maybe at that point, and like, because I was kind of glancing through their exercise of this. So they're just calculating like proton and electron differentials, and that starts getting pretty polarized. But then you're just talking about like two opposite charges, so.
Because you judge the dipole by basically just glancing through it as you're scrolling through. Is it like the distance between the actual atoms themselves?
Well, that would influence the dipole moment, yeah. So that's why in their kind of math of it, the more separated, right, the more extreme the dipole. But obviously, if they're in a covalent bond, you know,
That's
there's.
what I was looking at. It was looking like it was a difference between the polar, the distance,
Yeah.
and yeah, the magnitude, sorry, the distance of vector, and the position. That's fun.
Not too bad, though.
Numbers and fun are different.
You know, people shouldn't be so scared of math, though, and like, that's just something I've noticed in general. Is like, as soon as you look at an equation, people start shutting down. But it's like, you just gotta slow down, break it into its pieces.
Math is a puzzle, like, once you get it almost solved, someone just dumps a whole other puzzle onto your already almost finished puzzle, and then they mess it up again. Then you have to solve another puzzle, no, two puzzles in one, that's all jumbled up. So, that's my experience with math, at least. I'm like this close to finishing it, then someone dumps in the box puzzles, and yeah.
It means puzzle something is used the same 50 credit
So are all puzzles just the same then?
Most of them have the same cutout, so actually if you mix like 3 or 4 boxes of puzzles, there's gonna be 5 or 6 different pieces that fit together
Huh.
in the same spot. So they use like the same molds.
Yeah.
So they'll actually print the cardboard and then they just have a mold that comes out and chops it up.
That's pretty sick.
Yeah.
So now,
So
yeah.
it's really fun if you really want to play a puzzle, you can actually sit there and dump a bunch of puzzles together and try to make a whole new one by just putting them together.
Yeah.
What's really fun is if you flip them upside down and you just do the back of them. And
Oh
flip
my
them
God.
upside down, do the border without looking at it, and then you can flip it over and see what you get.
I got really creative ideas of fun. Alright, let's do another practice.
Okay, fish. Oh.
So I'm taking time to draw this. So just identify polar, non-polar. It's not that bad. It's just other than my handwriting being bad. But
Hey, are we gonna get a periodic table with the electron, the ionization numbers on them? Or should we print our own out? Would that probably be helpful?
maybe print your own out if you want one, because what I was planning, like if I was gonna make you do any electronegativity calculations, I would just say like, oh, the electronegativity of chlorine is blah, and this is blah.
Okay.
But if you wanted to like use it for reference for this stuff, if it helps, then you might want to print it. Or, you know, have like lecture notes handy, because it is apparently on this lecture slide.
Yeah.
I guess I could print it if people are really wanting it. I could print it in lab for you. So give people more time. Trying to think of more polar versus non-polar examples too.
This is only 2 answers. 2 possible answers.
It's true.
What level would you say calculating is that out?
Yeah, we don't do it in the 200 level. But I think the other issue is it's now just done computationally.
So there's no reason to ever have to calculate that.
Yeah. I mean, you could go through it though, honestly, in like a 200 level. Like, I think it's 200 level stuff because it's just like physics, like a direction problem ultimately. But I've never seen anyone actually work it out fully in any chemistry class. I've seen other things worked out painfully in higher level class.
So you just do that for fun.
Yeah, but basically now there's, and this is if you get really bored or if you want to take my 200 level class. So WebMO is a good like introduction to computational chemistry, and they have some free one. Yeah, so there's, I may be on the wrong site, or maybe I have to fill this in. I thought there was an online version. But anyways, you could run the computational stuff and it will spit out like a dipole moment when you run these calculations. So these are super easy for a computer to do. Where's the stupid WebMO online? Ah, this is what I was looking for, their demo server. Yeah. Yeah, people, this is just an open server, so people are just running random stuff. I was wondering if there's anything we could creep on that wasn't too. I just want to know what this is. Whoa.
Oh, that's cool.
I mean, people are.
Build what looks like, just curious, like, how do you build these things?
Well, all that is something didn't converge for some reason.
Oh, okay.
So
It-
it might not just bond together or something like that.
Yeah, usually what happens is like people draw the structure just too funky and then the computer can't handle it and then it's like takes it out to infinity, the molecules, and then it's like, I don't know.
Just self-destruct, no worries.
Yeah, but that's pretty common for this. Anyways, I think I would have to run our own calculation. I was trying to creep on anybody else's, but these are fairly large.
So do you think it's gonna make the design itself or does the computer optimize the design?
So it depends what you feed it. I just want to steal their water to see if I can look at the dipole moment. But basically, so like if you were doing this for a research setting, let's just see.
Geometry optimization.
I'm not familiar with what they're using. Okay, let's just see if this runs while we chat. But usually what you do is like, let's say you get a crystal structure of your molecule when you're doing research. So then you have like that crazy picture that we were just looking at. And then you can essentially feed the computer that crazy picture and then it'll kind of re-optimize the structure and then figure out like the MOs and all that. And let's see how it's calculated a dipole moment. It's kind of higher though than what we were just looking at experimentally or whatever they calculated. So, and that's where you go down the rabbit hole of how do the calculated dipole moments compare to real ones, and you know, compare everything. So it starts to get, and maybe my basis set wasn't correct. I just, you know, ran one to show you guys, but computational research would go into picking the right basis set to reflect your molecule to get the right results and blah, blah, blah. So that's the whole area. But yeah, it does give you a dipole moment. At least have some reference.
Okay.
All right, so polar, non-polar. We'll do, let me throw in.
So does a polar have to be absolutely zero on the dipole number?
Does a polar, or you mean non-polar?
Non-polar, that's what
I think the official definition is if it's less than 0.4 on the difference in electronegativity.
Okay, so that goes into, okay.
So that would be polar to have like different elements, not all one element?
Yep, so this one, you're correct, polar, so I would say that these bonds are pretty non-polar, but then we have these very polar, sulfur fluorine, so yeah, I like this. What about our acetone, is that polar, non-polar?
Well, I don't know exactly what the numbers are, but it has multiple difference, but it's really two bonds on the oxygen. I would say it's like non-polar.
So yeah, don't forget, right, oxygen does have those lone pairs, so that also makes it kind of negative, right? So probably more, so what do we think it is then? So polar, nonpolar. So yeah, it's more on the polar side. Even though it's a double bond and there's not too much of a difference, it's still pretty polar, and oxygen has those lone pairs, which makes it polar. Just looking for that unevenness. Yeah, so any like carbon-hydrogen bond is usually just considered nonpolar. Trying to find more data. Now I'm looking. Oh, I think it. No. No. Oh, here we go. So let's try another one. This might answer some other questions. So polar, nonpolar. Yeah, but they're still pretty close, relatively speaking. They're both halogens, though. Yep, so this is considered then nonpolar. So even though, right, we had a different group, it's not as different as a hydrogen. And so it's still pretty similar, and I wanted to get a number because you were kind of asking. And so according to some data I found, this has a 0.31 dipole moment. I don't know how accurate that is, but it's not crossing that one line we're kind of seeing with those other polar molecules. And it's still pretty low. It's like under 0.5. We'd probably have to calibrate our dipole moment scale with some other examples, but that at least kind of gives you a sense and a range. And
Looking at the actual numbers on the chart, it looked like the actual electronegativity numbers for chlorine was actually pretty big. That's why I was confused. Because you go from a 4.0 for chlorine to a 3.0 for chlorine, at least in the book. So you're almost a full one off. And there it's 0.8, which is still pretty strong.
How'd you get that 0.31? Aren't you just subtracting the fluorine negativity?
Oh,
from
the
fluorine?
0.31 just comes from like the internet. So we have to look that up. That somebody calculated the dipole moments.
But you're not just taking the fluorine electronegativity and subtracting the fluorine?
Not for the dipole moment. That's just we're looking at the individual bond. So you can do that. So let's do that to see kind of where we're at. So we have a difference of the fluorine and carbon of 1.43 versus chlorine and carbon.
You just added the fluorine and the carbon together?
Subtracted chlorine minus carbon.
And then subtracted that from fluorine?
Yeah, and not from fluorine. So this is carbon and fluorine, and this is carbon and chlorine. So
Oh, that's
first,
how you- okay, got it.
yeah, because his argument was analyzing each bond, right? And if you put that on an exam, I'm not going to fault you. So you could say, well, I analyze each bond. These carbon-fluorine bonds, obviously these are really polar at 1.43, right? And then our carbon-chlorine bond, so that's still considered a polar bond, though. And so that's just what I'm going off of, but if you wanna argue, there still is some unevenness.
Because both of those are polar bonds.
Right, yeah, so they're all
Or
polar,
covalent.
yes, they're all polar covalent, and, and this is why we're just kind of approximating it and going through it.
Because if you like just looked at that based off their sheet without like having calculations, they look off based off that you have one that's reporting different than the other two. That's why I was confused.
Yeah, and so that's why you at least have like a small dipole moment, right? Like you're not totally wrong is what I'm saying.
Yeah.
But it's just, we're just trying to classify them, so like we're fine calling this nonpolar if you want to make the argument that there's some polarity. You just want to write that out in a detailed explanation. So just, as long as you can explain your answer too, explain your rationale, and know what the process is you're trying to analyze both each bond individually, but then see, how does that overall add up? So, this is where the vector math comes into and why we turn to computational chemistry. So basically we could draw big fat arrows going out in all directions from the fluorine side, just trying to show that that's more polarized than maybe this chlorine bond. So then trying to quantify that, without doing the vector math is obviously difficult. I just kind of estimated as nonpolar going off of their halogens. That's all we're getting at, yeah.
So now I'm confused with the definition of polar, because the book is saying that non-polar means that it has equal pole everywhere, but then Google is saying that this one is polar. Is this just like some sort of exception, or?
So not exception, right? But that's where we get into trouble classifying things as a strictly polar, nonpolar, right? So I would still put this in the nonpolar category. I would more disagree with Google, but that's where we have to look at the dipole moment, because how the dipole moment is, and then also how does it behave? And so that's just like how solubilizing it is. So usually, there's like chemists have this order of solvents that they use going from like polar to more polar, and then you just, it all depends what you want to use, and then you just keep bringing out different reagents. So I don't know if I kind of confused more people.
So typically, if they're in the same column, it's going to be classified as like nonpolar because it's going to be mostly reactive the same way.
Yeah.
So it's going to be based more on how it reacts than what the actual like polarity of the number is. Yes, and a little bit of.
Yeah. Well, it's like we would want to in a ideal world look up the number, but you're not going to have that on a test, right? Where you can go look up Wikipedia and look at the dipole number, because the dipole number I think gives us the really best value, but we don't have that information, so that's why we just go off of those trends. But that's why if you look on Google, right, you might get a different answer than what we would expect just kind of eyeballing it, and it's not always clear either.
The one that I saw on Google, it had all those dots drawn out, and everything, it was like, it followed the octet rule, all of it. But I'm not sure.
Yeah, because, they all, and it would all just look the same, right? Because they're all halogens. So, right, you could do the same thing as what Google did. Right, you just add all the dots, but that doesn't really help us because they all have 8 dots around them because they're both halogens. So that's where I'm saying we need either computational chemistry or more data, but we don't have that luxury on an exam. And see, I'm also looking at, so if something is polar, you want to see, well, does it dissolve in water? And this has poor solubility in water, so that's why I would put it more at the nonpolar side, this trifluoromethane. So that's pretty low, but so more nonpolar things, right, are not soluble in water, and then polar solvents would be,
So then if something has a lone pair, that's gonna be polar as well,
yeah, well, that might hint towards that it's polar, yeah.
because it's gonna have a net, yeah, okay. Cause it's gonna have an uneven pull due to the fact that it has a lone pair.
Yeah, so like sulfur, dihydride is another example, so those lone pairs.
They're not gonna have as much of a pull.
Yeah, even ammonia, right, is polar because of that lone pair. This is non-polar. And so this is just again like kind of more orientation for yourself. So this is just another solvent. So this is called DMSO. I pointed it out because it's what I would call a big gun solvent. Personally, I don't like DMSO because it has a high boiling point. So once you add it to something, good luck getting it off. But I just wanted to point it out because it dissolves kind of polar and nonpolar compounds. But then, right, we're talking about, well, let's compare it to water. So it is soluble in water. So this kind of tells me, right, this solvent is going to be on the more polar side. It goes into water, so light dissolves light. So that's just another way to orient. And see, this one has a really high dipole moment. I don't understand this dipole moment. So this is 3.96 on the dipole moment, so that's pretty high comparatively. Yeah, so this is a pretty solubilizing solvent. Oh, and this is, I actually just heard about this fun fact. So I would not do this, but apparently if you get DMSO on you, then you would absorb DMSO through your skin and then have like a weird garlic taste in your mouth. But don't do that. I think a lot of things are bad for you. Let's see what it says about. What? It's an alternative medicine. I don't know about this.
No, it's an alternative medicine, so alternative to medicine.
Apparently it's a fake cancer cure, but that seems terrible. Let's see, toxicity. So LD50 of 7,000 milligrams per kilogram. So that seems like a lot that you could eat, but I wouldn't do it.
Well, if you like garlic, there you go.
Yeah, so I think the trouble with DMSO, or I mean, again, you shouldn't be playing with chemicals like that, but from what I've heard is DMSO can just help other things become solubilizing. So like if you get DMSO on your skin and then have some other toxins on your skin, it'll help those toxins really go through you.
Well, that might be why it's trying to say that it's not to increase the effects of blood thinners, steroid partners, and stuff, because it probably reduces or increases the blood membrane absorption.
Yeah, like it probably just increases, like if it's making everything kind of more soluble, because it's an awesome solvent basically. So yeah, it's just like solubilizing everything in your body in some way. So yeah, that would make your drugs more potent than if they're like more soluble running around.
I thought a company was persecuted for adding it as a preservative tells me everything I think I need to know.
I'm surprised you don't see that stuff at like, concerts, with like LSD and drugs. Can you imagine lacing LSD with DMSO and making it more potent and soluble?
You know, don't give people ideas. What? See, I don't know about those.
What? LSD is something that.
Oh, yeah, I heard about this case.
Yes.
Yes, yeah. It wasn't used also as like oven cleaner?
I wouldn't be surprised because it's a great solvent.
And that leads to the garlic taste because people were like saying they could taste like garlic or smell garlic. It's one of the two. But that explains why. It's because damn something. That's insane.
Yeah.
That's messed up, but it's insane.
Anyways.
Explosion hazard?
That's fun.
Acyl chlorides.
Yeah, acyl chlorides are pretty nasty. So anything, I think you're asking about something like this. So then it would be named as an acyl chloride, but
Make sure this information is great. See what the explosion? Here you go.
yeah, now we've gone.
Two
Anyways,
chemicals, low temperature. You got it.
chemistry is fun.
So is acetate acyl chloride?
Right, acetate though doesn't have a chlorine on there. So acetyl chloride would.
Okay.
So
That might have been the one that I was looking at.
yeah. So when
Instead of CH3COO, it's CH3COCl.
yeah, so this is probably your most basic acetyl chloride. I don't know too much about those. Yeah.
Has small drops of hydrochloric acid.
Yeah, so these would all be pretty nasty, as you can imagine, and tend to make HCl, and they're gonna all smoke too. So they'd be fun to work with, or angry to work with.
You don't mix with the other chemical.
Oh, they're great though to mix. Then you get a reaction
Well,
going.
I mean like the
That's old.
dimethyl sulfoxide will only lead to an explosion.
It depends on what explosion and what scale. But yeah, it's used. These acyl chlorides are used in esterification reactions. Anyways,
I mean, any explosion can be big enough if you use enough chemicals.
That's true.
Just a classification of a rapid expansion of
yeah.
heat and
Or
air. So, I mean, like, technically, what is it, calcium, or no, potassium is explosive inside the water. But if you put like a little chunk, it's not gonna blow your hand off. It might burn a little.
yeah.
What do you put a lot?
Then yes, you could blow your hand off.
Or just start a fire. Potassium fires
Or both.
are not fun to put out either.
You know, I have no experience with potassium fires. I've heard of electrical fires, grease fires, but never potassium fires.
You can't put potassium out with anything that has pure water in it.
Yeah, so have you heard of like those supercars and with like the electric supercars that burn and burn and burn?
Yeah.
So it's the same thing, except instead of potassium, right, they have lithium essentially. So they just have to let them burn because the firefighters come to douse water on it and it just burns even more. So
I heard that they can also just reignite themselves.
yeah, yeah, because they just react with the air again. So
That was the issue with the floods, when they were saying all those Teslas were raining.
oh yeah,
Spontaneously combusting. What was happening is they were breaking down the barrier of the battery, and then the giant battery, lithium battery, was bursting into flame.
yeah, it's kind of cool but kind of scary.
Scary driving.
It's
in a
cool,
way.
unless it's your
Waste of money.
Yeah.
Yeah, we won't even go into the other minerals in all those Tesla batteries, phones, like cobalt, artisan cobalt. Anyways, so we have 10 minutes. So what do we need to review? What questions should we go over? How are we feeling on things?
I think it's time conversation once I finish reading the book. Hopefully.
So we have a midterm on Monday?
Yes. I'm trying to pull up your midterm. No, you don't get a look. So let's see, there's so far, let's see, I can tell you what the old one is like. I haven't decided if I'm gonna change it or not. So the first question is just like classifying things as element, compound, homogeneous mixture, heterogeneous mixture. Number 2 is like a conversion question, but I give you like the conversion and they're not even real units. So watch out for that. Oh, we didn't talk about periodic trends. That's what we're missing. Because we're supposed to cover like ionization, energy, and radius, but we didn't quite cover that.
It does cover it in the book, and it even had a chart as well. That's pretty good.
So does that mean I can ask the question?
I mean, that's seems like it feasible.
I mean, if I'm being mean, I could totally ask the question if it's in the book. I just didn't cover it, which makes me feel bad.
I'll get people to.
Yeah, sure. We can also cover it really quick, because
Yeah, let's do it.
basically, ionization energy, right, increases as you go across the periodic table. And all that's from, so let's just compare like nitrogen versus fluorine, and the same argument is with the radius. So looking at their electronic structure, so if we fill in our valence electrons for nitrogen, so it has 5 versus fluorine, so 1, 2, 3, 4, 5, 6, 7. And so we say, again, since they're on the same energy level, so fluorine, if you're trying to, so ionization energy is just defined as ejecting an electron. And so obviously as you go across the periodic table and it gets closer to the octet rule, fluorine really doesn't want to give up an electron, right? It wants to gain an electron. So that means that fluorine has a higher ionization energy versus nitrogen. So nitrogen, it can give up an electron. Again, it's not too happy, but it's more favorable than fluorine. Again, we can see that since they're filling up. And then with the radius, so fluorine also has a smaller radius. So the radius also decreases as we go down, or across, I mean. So radius decreases across. And so why that is we can look at this same chart. So as you go across, you're filling up this 2p as you stay on that row. And so you're adding more electrons in the same distance away, since these are all, remember, degenerate. And so because of that, the attraction between the two, so your electrostatic attraction is stronger, since essentially you have more negative the same distance, so it gets smaller, so that like contracts your radius versus like nitrogen. So does that make sense for those? And then of course, right, ionization energy though decreases as you go down, since your radius gets bigger and bigger, so it takes less energy to remove it. So decreases, increases across. And of course your radius increases though as you go down. And we can also say, so either electron affinity or electronegativity. So we want to look at that trend. So fluorine is considered the most electronegative. So electron affinity and electronegativity increase as you go this way, so both across and up. But I won't go into the difference of electron affinity versus electron negativity. All right, so that's 3. Question 4 as it stands is just like plugging in some temperature conversions, so following a formula given.
By the way,
Question 5 is kind of some dimensional analysis and density. We'll see how that one goes. 6 is like figuring out protons, neutrons, and electrons. 7 is writing the electron configuration, except I write it in a way that's a little confusing, so you have to think about it though. And there's some naming, of course, or making formulas and names. Percent sand in a mixture, so that's kind of from lab. More electron configurations. And then drawing a Lewis dot structure. Which I may change that one to be a real molecule, but we'll see.
So is it like a 10 question?
It's, yeah, 12 questions. And then the last one is just calculating the atomic mass. So with the percent abundance, or sorry, calculating the percent abundance given the mass of 2 isotopes. So remember where you have to use the algebra. That's
Real quick, what was that formula again?
for figuring out the isotopes.
Yeah, it was, because it was only 2, and it was
So right, the,
X1 or
yeah, the basic principle
X plus.
is you assign one isotope X, right, the other isotope Y. You know X plus Y has to equal to 1 for 100%, which I just simplified to you have X, and then Y is equal to 1 minus X, and then you could set up probably the rest from there, so multiplying by the mass. So X times, then you're given the mass of isotope 1 plus 1 minus X times mass of isotope 2 gives you average mass. So that's probably the most basic way to write that. And so you'll have to solve that. All right, I think we're out of time. And we can, of course, talk more about the exam in lab if we need, but I at least gave you what each question is about. Probably won't modify the exam too much, if at all. Okay, other last minute questions, comments, concerns?
So I noticed that we had homework for chapter 4 and chapter 5. We just went over chapter 4 today, right? Or did we go over chapter 4 and chapter 5?
We just did chapter 4, so we'll probably save chapter 5.
Okay, sick, awesome.
Yeah, because that's what I was saying is I wasn't sure if we were going to hit chapter 5, and we probably should save it anyways since we got the midterm.
Okay, awesome.
And we'll just focus on 5 after.
I'll still read the chapter. I just want to.
Yeah, so midterm is just over chapters 1 through 4. So don't worry about that. And then we'll start chapter 5 a week from today. All right, I'm going to stop the stream and then